Good morning. Today we will continue our lesson on polarization. We were doing with the chapter 7, physical optics or wave optics, and we have already learned few phenomena of light like interference, diffraction, and we also had a discussion on polarization. Today we will see two new concepts related to polarization of light. The first one is double refraction by polarization. So let us see how this happens. Certain crystals like quartz, calcite or Iceland spar, when they are kept on some substances, like you can see a calcite crystal which is kept on a pencil here, how many images can you see here? How many images can you see of the pencil?
Two.
Two images. So this is because when light enters the calcite crystal and comes out, they undergo refraction. But the refracted rays divide into two, and the diffracted rays will be polarized. So instead of one single refracted ray, we are observing two refracted rays. One of the refracted ray which obey all the laws of refraction are called ordinary ray. And the other one which does not obey the laws of refraction is called the extraordinary ray. So from this figure, you can see here when unpolarized polarized light is incident on certain crystals like calcite, what happens is they get refracted and there are two different refracted rays. Both the refracted rays will be polarized in directions perpendicular to each other, and one of them which is obeying all the laws of refraction is called the ordinary ray, and the other one which does not obey the laws of refraction is called the extraordinary ray. Now when you see two images, how we can identify whether the image is made by the ordinary ray or the extraordinary ray? For that you have to rotate the crystal. Now, if you rotate the crystal, the image formed by the ordinary ray will remain stationary, and the image formed by the extraordinary ray will rotate with the crystal. So I told you before that we will see a video related to that. So let me just stop sharing here and we will go to another share. Okay. Can you see? Okay. Can you see the screen now? Can you see the screen now?
Yes, teacher.
Yes, teacher.
It's a YouTube screen.
Yeah.
Yes, teacher.
What I've got here is a bunch of calcite. This is
The
a cluster of calcite
volume
crystals. Here's another cluster of calcite crystals here. And
Yes, teacher.
I've got cleavage fragments. Now, I'm not going to talk about cleavage. I'm going to talk about a different physical property associated with calcite. It's actually an optical property, and it's called double refraction. And in order to see double refraction, you have to have a nice clear piece of calcite. So this is a pretty nice one. So we'll take a closer look and explore this concept of double refraction. Here's that piece of clear calcite. And what I'm going to do is put it on this piece of paper here so that you can see the effect of double refraction. All right, and put it down there. You should be able to see the doubling of the letters and the lines that I have written there. But also let me turn this around a little bit so you can see how they move about. Right, calcite is not unique in the effect of double refraction, but it is one of the minerals that shows it the best. Let's try another side here. Of course, the thicker the piece and the clearer the piece, the better the effect will be. All right, so that's an example of double refraction in the mineral calcite. This is another ROM of clear calcite that shows double refraction very nicely. In order to explain the process of double refraction, we're going to take a look at the calcite at an atomic level. This green rectangle here will represent the cleavage ROM. An ordinary beam of light actually vibrates in two directions at the same time. There is a horizontal component called the ordinary ray and a vertical component called the extraordinary ray. An ordinary source of light like the sun or an incandescent bulb will actually produce this sort of light vibrating in two directions at the same time. So here comes a beam of light passing through the calcite crystal structure. All right, this is the path of the ordinary ray. Notice that as it enters into the calcite, it is bent or refracts. Now, the extraordinary ray passing through the calcite is also refracted, but it is refracted more. So there are two beams of light. One that is vibrating in a vertical direction, and the other beam of light, shown there, is vibrating in a horizontal direction. What the calcite is doing is splitting the beams of light, and the light coming out is actually polarized light. Polarized light simply means that the light is vibrating all in the same direction, either as the ordinary ray or as the extraordinary ray. Now, this is the atomic structure of calcite, and you can see that it consists of blue calcium atoms, red oxygen, and the purple ones there are carbon, and that it is a very geometrical structure. Right? Now, it is this sort of structure that interferes with the passage of the light. So here's the vertical beam of light passing through there, and you can see there's lots of atoms for this thing to interact with. As a result, this particular beam of light is slowed down. The horizontal component is also being interfered with by the structure of the calcite, but not as much. So the vertical beam is slowed down more than the horizontal, and this results in the splitting of the beam. So again, there are the two beams passing through there, and we end up with two beams of polarized light, both at 90 degrees to each other, right? The extraordinary ray and the ordinary ray. To demonstrate this concept of polarized light coming out of the calcite from the ordinary and the extraordinary rays, what I've got here is a polarizing filter for a camera. And I'm going to hold it up in front of the camera here so that you can see the effect of blocking out one of the vibrational directions. So let me bring it up a little closer to the camera lens and get around here a little bit, and I'll just rotate it. All right, so you can see just one single calcite, and I'll just...
Yeah, I have a question here. Can you tell why, when he rotates this camera lens, it's we can't see one image and we can see sometimes one image? Can anyone of you tell me? What is this lens acting as? The speed.
Analyzer.
Yes, definitely. It's an analyzer. So we know that when the analyzer and the polarized direction is same, what happens? It will pass through. But when he rotates, it becomes 90-degree with the polarized direction. Then we can't see. So that's why when he used the analyzer, we see sometimes double image and sometimes single image. Okay, that's right.
Just turn it a little bit more, that one disappears, and another one. So what we're seeing here is a result of blocking one of the vibrational directions out with the polarizing filter so that the other one passes through. Right? The polarizing filter just blocks out one of the vibrational directions, and every 90 degrees it'll block out one and allow the other one to pass through. Double refraction in calcite.
Okay, is that clear to you, the concept of double reflection?
Yes, teacher.
Okay, so let's go forward now. And we were discussing double refraction, right? Now, there is another concept which is also related to polarization. that explains, or another law which explains what happens to the intensity of light during polarization. So there is a law called Malus Law which explains what happens to the intensity of light during polarization, and also after polarization when it passes through the analyzer. The intensity of light coming out of the analyzer depends upon the angle between the polarizer and the analyzer. Here you can see the unpolarized light, right? It's in all directions. And when the unpolarized light passes through the polarizer, what happens? Vibrations in one direction is cut off, and the vibrations will be only in a particular plane. So here, all these vibrations which are in all directions are resolved into along the y-axis, and we can say along the z-axis. If we consider this as the y-axis and this as the z-axis, so all of them are resolved, and we see that only the vibrations in the y direction is there, all the vibrations in the z direction is cut off. Now, when the unpolarized light passes through the polarizer, what happens is its intensity becomes half, because half of the energy is cut off. Suppose this unpolarized light have an intensity with magnitude 50. What will be the intensity of this polarized light?
25.
25. So first of all, when it gets polarized, its intensity becomes half. And that intensity of the polarized light is expressed by I naught. So don't mistake I naught as the intensity of the unpolarized light. It is just half of the intensity of the unpolarized light, and it is expressed by I naught. That is the intensity of the polarized light, and the corresponding amplitude is expressed as A naught. Okay, usually the intensity is related to the square of the amplitude. Intensity changes as the square of the amplitude. Now, when you pass this polarized light through an analyzer, you know that if the angle between the polarizer and the analyzer is 0, then all the light will pass through that. Okay? And when the angle between the polarizer and the analyzer is 90°, you can see no light coming out of analyzer. So according to the angle theta, the light coming out of the analyzer changes. So what is the trigonometric function which gives you a value 0 when the angle is 90°?
Cos.
Cos. And so we have a tendency to think that the intensity of the wave coming out of the analyzer will depend on cos theta. So Malus law states that the intensity of the polarized light transmitted through the analyzer varies as the square of the cosine of the angle between plane of transmission of the analyzer and the plane of the polarizer. So the intensity of the light ray coming out of the analyzer is proportional to the square of the cosine of the angle between the polarizer and the analyzer. So you have to learn this. It is proportional to cos square theta, or you can write I is equal to I naught cos square theta. So I naught is nothing but A naught square. I naught is A naught square because intensity is equal to amplitude square. So you can write I is equal to I naught cos square theta. This equation you will have to memorize. It will be useful for solving problems. Also, remember that I naught is not the intensity of the unpolarized light, but it is the intensity of the polarized light. Is this clear to you, Malus Law? I
Yes,
can.
teacher.
Yeah. Okay, now let us see, according to this law, how the intensity of light varies with the angle between the polarizer and the analyzer. So this is a graph where along the x-axis, angle between the polarizer and analyzer is taken, and along the y-axis, you have the intensity of light coming out of the analyzer. So when the angle is 0, you know, cos 0 is 1. So the intensity will be maximum, or it will be equal to that of the polarized light. So it is maximum here. Now, as the angle increases from 0, what happens? The intensity decreases. And when the angle between them becomes 90, what happens? The intensity of the light coming out of the analyzer will become 0. Again, when you continue rotation and it becomes 180-degree, what happens? Again, the intensity of the light will be maximum, as we saw in the previous video, that when he rotates the analyzer, the you can see one image and it diminishes, and the other image appears, then it diminishes and the other image appears. This is because the intensity of the a light ray coming out of the analyzer varies as we rotate the analyzer. Is this part clear to you?
Yes, clear.
So that's the end of this lesson, that is wave optics. And we have, I hope all the concepts we have discussed. And